Hey there, and welcome. If you're revising the particular nature of matter, you have come to the perfect spot. We're going to break this all down in a super quick 5-minute explainer to get you totally ready for any test. All right, let's just jump right in.
Okay, first things first. Let's start with a really big question. Just look around you, right now. Your chair, the air you're breathing, even you. What is all of that stuff actually made of?
And you know what? The answer is actually pretty simple. Everything, and I really do mean everything, is made of these impossibly tiny particles that are always moving around. And that one idea, that's the key to unlocking everything we're going to talk about today.
So here's what we're going to cover. We'll nail down what matter is, check out the properties of particles in solids, liquids, and gases, see how they switch from one state to another, understand the energy changes, and we'll finish up with diffusion. Sounds good? Let's do it.
All right, section 1, let's get the basics down. What do scientists even mean when they use the word matter? It's a word we hear all the time, but the scientific definition is super important.
Okay, so in science, matter is basically anything that has mass, the amount of stuff in it, and takes up space. But here's the part you really need to remember. It's made of tiny particles that are in constant, random motion. That little detail is going to explain everything else.
Okay, so if everything is made of these tiny moving particles, then how on earth do we get three totally different things like solids, liquids, and gases? Yeah, this is the big question, right? If it's all the same building blocks, why does an ice cube feel so different from a glass of water or the steam coming from a kettle? Well, it all comes down to two things: how the particles are arranged and how much energy they have.
So here's a good way to picture it. In a solid, the particles are all neat and tidy, packed together in an orderly way. They're stuck in place, just vibrating a little bit. But in a liquid, while the particles are still packed close together, it's more of a jumble. They're disorderly, and they can actually slide right past each other.
Now let's bring gases into the mix. In a liquid, strong forces hold the particles together, and they don't have a ton of movement energy. That's called kinetic energy. But with a gas, it's a whole other story. The particles have so much kinetic energy they completely break free. They're miles apart from each other with really weak forces between them, just whizzing around all over the place.
And you see, how these particles behave is directly linked to the properties we can actually see and measure. A solid keeps its shape because the particles are locked in place. A gas has no definite volume because its particles just spread out to fill whatever container they're in. Honestly, this table is like the perfect cheat sheet for revision. Okay, let's zoom in on one of these properties. Why is it that you can squash a gas, but you can't really do the same for a liquid or a solid? What's going on there?
It really is all about the gaps. You can compress a gas because there's tons of empty space between the particles. You're just squeezing them closer together. But in solids and liquids, the particles are already packed in tight. There's just no more room to squish them. And that same logic explains density, too. The more closely packed the particles are, the higher the density. Simple as that.
Okay, so we've got our 3 states down. But of course, things don't just stay in one state forever, right? They can transform. And the secret ingredient to make them change? Well, it's all about energy.
Let's just imagine we have a piece of ice, and we start heating it up. As you add heat, you're giving those particles energy, and they start to vibrate like crazy. Eventually, they vibrate so much they break free from their fixed spots, and that, right there, is melting. If you keep adding heat, the liquid particles move faster and faster until they finally have enough energy to escape altogether and become a gas. That's boiling.
So let's quickly nail down these key terms. Melting and boiling need to absorb heat to work. Freezing and condensation happen when heat is released. And don't forget the cool one, sublimation. That's when a solid, like dry ice, turns straight into a gas, totally skipping the liquid phase.
So, we can actually visualize all this. And that's where something called a heating curve comes in. It's an awesome way to see what's really happening with the temperature as a substance changes state.
Think about it. When you boil water, the temperature goes up and up and up until it hits 100 degrees Celsius. And then it just sits there, boiling away but not getting any hotter, even though you're still adding heat. So, what gives? Why doesn't the temperature just keep climbing? Okay, here's the big secret. When a substance is changing state, the energy you're adding gets a new job. Instead of making the particles move faster, which would raise the temperature, its entire mission is to break the forces holding the particles together. Once all those forces are broken and the change is complete, then the temperature can start to rise again. Okay, last section. Let's talk about the absolute best proof we have that particles are always moving, even when we can't see a thing. It's a process called diffusion. So what is diffusion? Put simply, it's just the natural movement of particles from a place where there's a lot of them, a high concentration, to a place where there are fewer of them, a low concentration. They just spread out. And the reason this happens, well, it goes right back to the very first thing we said. Particles are always in constant, random motion. They just can't help but bump and jostle their way around until they're spread out evenly. Think about it. If someone sprays perfume in one corner of a room, a few moments later you can smell it clear across the room. That's not magic, my friends. That is diffusion in action.
And that's a wrap. From how particles are arranged to how they change state and spread out. So my final question to you is, now that you know all this, where are you going to see it in action next? Maybe when you drop a tea bag in hot water, or when you can smell dinner cooking from another room. The proof is literally all around you.